Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 14, the transport layer. Pretty simple concepts, not hard to understand. If you are watching this live with me, please hold your questions for the end of the presentation, and I will give you an opportunity to ask them. If you are watching this as a recording inside of our NetAcad class, please ask questions inside of our help discussion forum. And if you're watching this question inside of YouTube, please ask your questions down below in the content, below the content window, and I'll do my best to answer your questions in the content, in the comment section, and feel free to help each other out as well. All right, Module 14, the transport layer. Okay, in this presentation, I'm going to compare the operations of the transport layer protocols in supporting end-to-end communication. I'll explain the purpose of the transport layer in managing the transportation of data in end-to-end communication. I'll explain the characteristics of TCP and UDP. I'll explain how TCP and UDP use port numbers. I'll explain how TCP establishes sessions and terminates sessions to facilitate reliable communication. I'll explain how TCP protocol data units are transmitted and acknowledged to guarantee delivery. I'll compare the operation of transport layer protocols in supporting end-to-end communication. We'll start with the transportation of data. So the transport layer is responsible for logical communication between applications running on different hosts. The link between the application layer and the lower layers that are responsible for network transmission. So here we see the transport layer, and it helps the data move between the application layer and the network and the lower levels of the devices of the OSI model. The transport layer has the following responsibility. It's tracking individual conversations. It segments data and reassembles those segments. It adds header information. It identifies, separates, and manages multiple conversations. It uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. So in this picture, you can see the different types of media, email, instant messaging, web pages, online video, streaming video, all of those different multitasked operations, because when you're on the internet, you're using the computer, you're doing many things at one time, and all of those need to transmit data. And so what the transport layer does is it segments that data, it labels it, and it identifies it, and then it interleaves that data with all of the other pieces of data and sends it out or through the bottom layers of the OSI. When it comes back the other direction, it then separates that data and sends it to the correct application on the higher layer. IP does not specify how the delivery or transportation of the packets takes place. Transportation layer protocols specify how to transfer messages between hosts and are responsible for managing reliability requirements of a conversation. The transport layer includes TCP and UDP. That's what you need to learn about at this layer. TCP and UDP, you need to know the differences between the two. Right here on this level, on this slide, it shows you that TCP is responsible for FTP, HTTP, SMT, and possibly DNS. UDP could also be DNS and TFTP, and we'll get much deeper into the applications as we move through. Now, TCP provides reliability and flow control. TCP basic operations include numbering and tracking data segments transmitted to a specific host from a specific application, acknowledging received data, retransmitting any unacknowledged data after a certain amount of time, sequencing data that might arrive in the wrong order, and sending data at an efficient rate that is acceptable by the receiver. So in that case, it's sort of like when you're talking to somebody and you say a whole bunch of information and they're like, can we take that step by step? That's what we mean by reducing or increasing the speed of the transfer. Let's just briefly look at this picture. And this picture shows the fact that a file sent to a server using File Transfer Protocol, FTP, could use multiple paths to get through the internet to get to FTP. During that path, what happens is what we're going to describe. When it gets to the other side, we're going to describe what happens whether using TCP or UDP. Now, this is TCP. It actually guarantees that all of the data, all SIG segments make it to the FTP. That is TCP guarantees that all of the data, if it doesn't make it, then it retransmits and before it finishes the process, it makes sure all of the data is there. And I'll explain how. UDP, on the other hand, provides the basic functions for delivering datagrams between the appropriate applications and very little overhead and data checking. UDP is a connection-less. TCP is connection-oriented. It builds a connection, and that connection stays there until all of the data has been acknowledged on the other side, and then it shuts itself down. And I'll show you how to do that, how it does that in a little bit. UDP, on the other hand, is connection-less, just like FM radio. This is like FM radio. When FM radio transmits its beacon of your favorite radio station, it does not know if your radio is on, if it does not know if you have your radio on in the house, in the car, has no idea. It is just constantly transmitting the FM signal. When you turn on the radio, it's there. There's no guarantee that it's going to be perfect. If you ever listen to AM radio, you know, that signal comes and goes from long distance conversations in AM radio. Remember TCP, which is reliable, is connection oriented. UDP is connection-less. It's known as best effort, meaning that there's no acknowledgement. It just does its best to try to send the data out there, just like FM. It does its best to send the signal. So a file sent to, in our illustration here, a file sent using trivial file transfer protocol, it just sends the file. If the file does not make it where it belongs, then the only way for the sender to know is if the application layer of the sending computer, this server over here, this server sends a message back saying, hey, I didn't get that file. But, or you check and it's not there. But UDP just sends the file. Even on the other end, it doesn't reorder the data. It just passes the data along. And we'll explain why just now, I think. So UDP is also used by request and reply applications where the data is minimal and the retransmission can be done quickly. If it is important that all of the data arrives and that it be processed in its proper sequence, you can't use UDP, you have to use TCP. So you're banking on a secure HTTPS connection is absolutely TCP, because you can think that the bank wants to make sure that you have a session created, all of the data is transferred, and then that the session is brought down to make sure that, you know, you get $100 and they make sure you record $100, right? So let's look at these diagrams here. We have UDP is great for things that just need fast data, like voice over IP, DNS, streaming video on a YouTube video would be all UDP. It sends the information. If it gets to you, great. If it doesn't get to you, it doesn't resend, and there's no acknowledgement. It's fast, there's low overhead, it does not require acknowledgements, does not resend lost data, and delivers data as it arrives. Now, where it says it does not resend lost data, UDP doesn't resend the data, but the data may be requested and an application might request it. TCP, on the other hand, for example, SMTP, email, you want to get the whole email, right? Not parts of it. HTTP, HTTPS, the website, you want the whole website, not just part of it. It requires the protocol properties include reliable, acknowledging the data, resending lost data, and delivering data in sequential order to the application layer above it. Let's talk about TCP in depth. So TCP establishes a session. TCP is connection-oriented protocol that negotiates and establishes a permanent connection or session between the source and the destination device prior to forwarding any traffic. It ensures reliable delivery. For many reasons, it is possible for a segment to become corrupted or lost completely as it is transmitted over the network or the internet as a whole. TCP ensures that each segment that is sent by the source arrives at the destination. It provides same order delivery because networks may provide multiple routes that can have different transfer rates. Data can arrive in the wrong order. It also supports flow control. Network hosts have limited resources, memory, processing power, etc. When TCP is aware that these resources are being overtaxed, it can request that the sending application reduce the rate of data transmit or expand the rate of data transmit. If the transmissions are successful, it may try to expand that packet, the amount of data that's sent, the MTU size. And I'll come back to that in a little bit, so don't worry about that now. TCP is a stateful protocol, which means it keeps track of the state of the communication session. TCP records which information it has sent and which information has been acknowledged. So the different fields include the source and destination address to identify the source application by port number, the source port and destination port. The sequence number, that's a 32-bit field used for data reassembly purposes. Think about the order of things or the sequence of things. The acknowledgement number is a 32-bit field used to indicate that data has been received and the next byte expected from the source. I'll show you the acknowledgement in a little bit. We call it an ACK. The header length is a 4-bit field known as the data offset. This indicates the length of the TCP segment header. Reserved, it's just reserved for future use, that 6-bit field. Control bits are used to indicate bit codes or flags which indicate the purpose or function of the TCP segment. Window size is a field used to indicate the number of bytes that can be accepted at one time. I mentioned that earlier, and I'll talk about it again later. Checksum is for error checking, and urgent allows the packet to be marked, indicating that it contains data that is urgent in nature. And it's 20 bytes, and this is what I was just reading, if you were wondering. And here it is in action. So IP at the lower level, that would be IPv4, IPv6. So we're talking the network layer. And it sends information to TCP, well, if it's TCP oriented. So TCP includes tasks associated with dividing the data stream into segments, providing reliability, controlling data flow, and reordering segments for HTTP, FTP, SMTP, SSH, all examples of TCP protocols. Now, UDP features include the following. Data is reconstructed in the order that it is received. It is sent to the level above in the order that it is received. Any segments that are lost are not resent. There is no session established. The sender is not informed about the resource availability, so it does not change the size of the MTU. The UDP header is far simpler than the TCP header because it only has 4 fields and requires 8 bytes instead of 20. The source and port numbers, the length of which is a 16-bit field that indicates the length of the UDP data header, the checksum for error checking of the packet, and then the application layer data, which is the actual data itself, which varies, of course. That's what's coming downstream from or heading to an application. That's the actual data. Now, this UDP includes things like DHCP, DNS, SMTP, Trivial File Transfer Protocol, VoIP, and video conferencing. Those are all UDP. Remember, connectionless, and think anything that requires little or no delay. For example, video streaming, voice, those are the kind of things that go, or anything small like SMTP and I'm sorry, SNMP and TFTP. Port numbers. Now, TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. The source port number is associated with the originating application on the local host, whereas the destination port number is associated with the destination application on the remote host. When we're talking about this, I want you to realize they're talking about multiple simultaneous conversations, right? Multiple simultaneous conversations. So the perfect example for this is my wife. My wife knows how to use the internet, but she does not know how to, or does not choose to, or just forgets to close web pages. So she will continuously open new web pages, page after page after page. So I have a browser open. I might have 2 or 3 or 4 web pages open at a time, and I switch between them. And when I don't need one, I close it. And TCP is handling knowing which data is going to which web page. So if I have four different Firefox pages open, it will know where to send the data between those 4 ports, pages. That's why it uses, we'll see in a minute, it uses ports in the upper range. I'll explain that. Don't worry about it. My wife, on the other hand, she has opened up so many websites at one time that it's taxed the resources on her computer. And she has 16 gig of memory. She has opened so many pages that each page, each tab is only 1 centimeter or half a centimeter wide. She can't see what all this, and then she has to click on all of them. Well, anyways, so having all of it's okay. You can TCP will make sure that the right data goes to the right page all the time without a problem, but there's no need to do that. You really should close out websites when you're no longer using them. And no matter how many times I tell her, she doesn't close those pages. So some of you might be like that. Start closing your pages when you're done. It's easier to find. Now, the source and destination ports are placed within the segment. The segments are then encapsulated within an IP packet. The combination of a source IP address and a source port number is, or the destination IP and the destination port number is called a socket. So here we see the source port and the destination port. This is a socket. This coming back, this is, I think that's coming back. Oh no, it's just 2 different types of data. So we have FTP up here, the source port and the destination port, and then down here, this is a web connection, the source port and the destination port. The combination of the source IP address and the source port number, or the destination IP and I already read that. Sockets enable multiple processes running on a client to distinguish themselves from each other, and multiple connections to a server process to be distinguished from each other. Again, the multiple websites is the perfect example. They're all 80. They're all going to web servers 80 or 88 or 443. They're all websites, but the port will change. So when the data comes back, the socket identifies which one of those tabs the data, which one of those web pages the data is destined for. Now, there are well-known ports, and there's a list of those. These ports on the next page, these port numbers are reserved for common or popular services and applications such as web browsers, email clients, and remote access clients. Defined, well-known ports for common server applications enables clients to easily identify the associated service required, and for you and I to know what the data is. Now, this is a list of some port numbers in the well-defined range, which is 0 to 1023, which just happens to be the last four of my phone number, which makes it really easy for me to remember. These are a list of those ports, and you can recognize file transfer protocol, FTP, is data is 20 and control is 21, secure shell is 22, telnet is 23, on and on and on. It goes down the list. These are all the port numbers. Now, I strongly recommend, if you have yet to take the CCNA and it's something that you want to do in the future, you need to memorize these. Don't memorize them just at the end when you go to take the test. You might as well make the flashcards now, indicate the port on one side and what it actually is on the other side. Maybe even throw in a UDP TCP so that you can maybe port and protocol port. Maybe that's one set of flashcards, and maybe port an application or protocol an application so that you can quickly know if you see SMTP, whether that's TCP or UDP, and then another card tells you, by going through those flashcards, you can know telnet is 23. Anyways, you need to know those because you'll be expected just to know what port different data is on, and this is a great, flashcards are a perfect way to learn that. Anyways, those are common ports that you should know. You don't have to know all 1023. At one point, I had a picture of all 1023, but most of them are not ports that really are well known by you or me. Computers are well known, and also there's a bunch of old well-known ports that are no longer used. So I'm not going to try to remember any of those, but they're still in the list. If you go through the list and look at them, they're going, oh yeah, I remember we used to use that. Well, the port is still for that purpose. It's just not, they're not going to retire the port or reassign it, because then computers would be confused, I guess. I'm going with that. Now, there's also registered ports. That's from 1024 to 49,151. These port numbers are assigned by IANA to a requesting entity to use with specific processes and applications. These processes are primarily individual applications that a user has chosen to install rather than the common applications that would receive a well-known port number. For example, Cisco has registered port 1812 for its Radius service authentication process. Now, there's also the upper range from 49,152, the next port, through 65,535. These are private and or dynamic ports. These ports are also known as ephemeral ports. The client OS usually assigns port numbers dynamically when a connection to a server is initiated. The dynamic port is then used to identify the client application during the communication. This is that port that that is usually, and I will see an example in a little bit, but this is a port like 51,172 connected to an 80 makes a socket that identifies one of the HTTP websites that my wife currently has open on her computer. And then 63,225, random number in that range, is the second web connected to 80, is connected to the second website. And then when the data comes back, it's easily identified. It goes to the right website. I kind of kicked the dead horse there, I think. All right. So you can see some of these sockets being made by going to netstat. Unexplained TCP connections can pose a major security threat. Netstat is an important tool to verify connections, and you can see each one of these addresses, 192.168.1.124, connected to a port. That would be local, and this would be foreign, a foreign port. And you have a connection established. Those are the connections, the TCP connections, where data is being transferred back and forth. Okay, hopefully that helps to explain a couple things. And this is one way to find out if some people are not unauthorized to use your computer, I suspect. I haven't ever used it for that, but you could. Now, the TCP server process. Each application process running on a server is configured to use a port number. An individual server cannot have two services assigned to the same port number with the same transport layer services, within the same transport layer services. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and processes segments addressed to that port. Any incoming client request address to the correct socket is accepted, and the data is passed to the server. All right, well, that's a lot of words. Let's see what it really means, okay? So here we have, for example, the client. The client is doing an HTTP request on source port. The source on client 1 is 49,152, one of those upper range addresses, and its destination is 80. The server's port, the server's port is port 80. That is a web request, right? On the other side, client 2, the server can handle more clients. The server is talking to this client, and this client is asking for an SMTP request. It's using 51,152, again in that upper range, and its destination is port 25, which is SMTP. So the client is requesting using this socket for SMTP. This client is requesting using this socket for HTTP. Now the server receives the HTTP request and the SMTP request. It flips that data and then returns the payload along with the destination. Now the destination at this point, coming from the server to the client, it goes there with the destination port 80. The server switches it, so now the destination is the source port 59,152. When client receives the HTML data on port 49,152 from port 80, it knows which website to give that data to. On the other hand, the other side, it flips these two, and now the destination is 51,152. The source port, its port, is 25. It sends it to client 2. Client 2 looks at the destination port and says, oh, I've got that socket open. I'm going to go ahead and connect to the right SMTP server and process, and it gets the data, and then it closes the packet, and we're done. That socket is open until in TCP, that socket is open until the communication is complete. Okay, hopefully that's not hard to understand. I think it's pretty clear. A little bit like the way it flips it is like source and destination IP addresses, right? You send it to the destination from your source IP, destination IP, gets to the other side, it flips it, sends it back. Same idea, except we're talking about source port and destination port, and we're talking about TCP and sockets instead of IP addressing. Now, as I mentioned again a moment ago, it opens a connection, and that connection stays open until all of the data has been transferred. The initiating client requests a client-to-server communication session with a SYN. The computer B in this case receives the SYN and then acknowledges the SYN and sends its own SYN, and then computer A sends an acknowledgement acknowledging that SYN, and then it sends an acknowledgement back to B. I'll show you that again in a moment and why it's a three handshake message right now. No, this is to finish it. So this is to start it. A SYN, a SYNAC, and then an acknowledgement. A SYN, a SYNAC, and an acknowledgement of the ACK. It's already sent a SYN. It doesn't send a SYN again. If I said that a moment ago, I apologize. It's a SYN, a SYNAC, and then a SYN. Then an ACK. Did it again. Anyways, let's go to the next page. To finish, it's the same thing. It sends a FIN. Now, on this side, it also sends a FIN, and it sends an acknowledgement that it received that FIN. On this side, we just acknowledge that we've received the FIN. So this is the FIN, a FIN-ACK, and then an ACK. Same idea. We see a video in a little way that actually takes you to a packet and shows you, if you can stay awake through the video, it shows you the SYN-ACK and that handshake that happens. Now, TCP Three-Way Handshake. The functions of the three-way handshake. It establishes the destination device is present on the network, that it's open and available. It verifies that the destination device has an active service and is accepting requests on the destination port, and that the initiating client intends to use. So port 21, port 80 is open. Firewall could prevent those ports to be open, although I can't imagine preventing the web traffic to be closed, but it could. It informs the destination device that the source client intends to establish a communication session on that port number. After the communication is completed, the sessions are closed and the connection is terminated. The connection and the session mechanisms enable TCP to reliably function. Now, there are 6 flag bits that are set in the control. It includes URG, acknowledge, PSH, RST, the SYN, and the FIN. We'll see a video that sort of covers some of that data. So let me go ahead and pause my recording. I'm going to pull up that video, and then I'll pull it up. So one second. All right, I've queued up that video. Let's go ahead and watch it.
I have some screenshots of a Wireshark packet capture that shows the process of a TCP three-way handshake and the termination of a TCP conversation. Let's analyze these screenshots to get an idea of how it's working. TCP is a connection-oriented protocol, meaning an end-to-end connection needs to be established first before data can be sent or received. The TCP three-way handshake initiates that connection. When the connection finally needs to be terminated, for instance, let's say it's a connection to a web server and you close the web browser, the connection is terminated with two-way handshakes. A TCP three-way handshake involves 3 steps: a SYN and an ACK, and an ACK. SYN stands for synchronization, and ACK stands for acknowledgement. First, the initiating host sends a synchronization segment. The responding host sends an acknowledgement and its own synchronization segment, and then the initial host sends an acknowledgement segment. Hence the SYN and an ACK, and ACK. We can see that here at the top of this screenshot. If we look at the packet list window at packets 10, 11, and 12, we can see a SYN and an ACK and an ACK. This is the three-way handshake. If we look at the initial packet in the three-way handshake, the SYN segment up here at the top, we can see that the sequence number is 0. The beginning of a three-way handshake is sequence number 0 because it's the first packet in the connection or conversation between two hosts, or in this case, a host and a server. The sequence number is actually a 32-bit random number called the ISN, or initial sequence number. This random number, or ISN, is chosen randomly at the beginning of each TCP conversation. This helps to protect against TCP connection hijacking attacks. Wireshark takes that 32-bit random number and converts it to 0. It then increments the sequence numbers and the acknowledgments from there. This makes it easier to read and follow the segments in order using the Wireshark program. Let's look at a few of the details for this initial SYN segment. We go down to the packet details window, and we can see sequence number 0, that it's the relative sequence number. If we look at the flags, we see that the SYN bit has been set. You can see it here with a 1. In the next packet, packet number 11, the server responds to the initial synchronization segment. I'll go to the next screenshot, and now packet 11 is highlighted. The server responds with an acknowledgement acknowledging sequence number 0 and sending acknowledgement 1. So the initial sequence number with relative sequence number 0 has been incremented and acknowledgement 1 has been sent. We can see in the protocol details window acknowledgement number 1, and that it's the relative ACK number. The server has also sent its own synchronization segment, and that number is 0 since it's the initial conversation going the other way. If we look in the details window, we can see that the sequence number is 0, and that's a relative sequence number from the server to the host. If we look here at the flags, both the SYN bit and the ACK bit have both been set. If we go to the next screenshot, in packet 12, which is step 3 in the three-way handshake, host 10.1.1.1 responds with an acknowledgement or ACK. And if we look in the protocol details window, we see the acknowledgement number is 1, incrementing the server's synchronization segment by 1. You can see here that the acknowledgement bit has been set, but notice that the SYN bit has not been set. This is the final phase in the three-way handshake. Let's take a look at how the TCP connection terminates. I'll go to the next screenshot, and you can see in packet 16, the server is communicating to the host at 10.1.1.1 and has sent a segment with a finish or fin and an acknowledgement or ACK. In this segment, we have a fin and an ACK. The fin ends the conversation. The acknowledgement flag has been set since the three-way handshake was first established. And in every segment sent thereafter, the acknowledgement flag is set. You can see that in the next packet, packet number 17, the host has replied to the server with an acknowledgement acknowledging that the conversation has ended. This is a two-way handshake, a fin and an ACK and an ACK. If we look ahead in the packet list window to packet 18, you can see that host 10.1.1.1 then sends the server its own fin and acknowledgement, and then the server replies with its own ACK. So you have two-way handshakes to terminate the connection. If I go back to the previous screenshot and take a look at the protocol details or the packet details, we can see here in the TCP segment the flags. Notice the 1 for the acknowledgement, and then the 1 for the finish or fin flag here that's been set. Notice that the acknowledgments went as high as number 374, indicating that these screenshots were probably generated from two separate packet captures in Wireshark. You can see in these last two screenshots how the conversation ends with two two-way handshakes, a fin and an ack, and then another one going the other way.
All right, so hopefully that helps clarify that communication that I was mentioning just a few minutes ago. So the next thing we're going to talk about is reliability and flow control. Now, TCP offers guaranteed and ordered delivery. TCP can help maintain the flow of packets so that devices do not become overloaded. There may be times when TCP segments do not arrive at their destination or arrive out of order. All of the data must be received, and the data in these segments must be reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. In this case, in this diagram, we have 6 segments of data that are being sent over the network. At the other side, those 6 segments are received out of order, 1, 2, 6, 5, 4, 3. It's TCP's responsibility, or a role of TCP, to reorder those segments 1, 2, 3, 4, 5, 6 before it sends it to the application layer. Here is a video depicting the simplified example of TCP operations. It's 14. If you're using the website itexamanswers.net, it is video 14.6.2. 14.6.2. And let's watch this.
This video depicts a simplified example of TCP operations. It is not necessarily a realistic depiction. TCP is a connection-oriented protocol in that a connection is established first using a three-way handshake before data is sent. Another characteristic of TCP is that it's a reliable protocol. Two things that make it reliable are sequence numbers and acknowledgments. Every TCP segment that's sent in a TCP conversation gets a sequence number. So every byte of data is numbered basically in a sequential list. This allows a receiving host to rebuild the data from the ordered numbered segments. If data arrives out of order at the receiving end, the data can be put back together in the proper order thanks to the sequence numbers. Acknowledgments come into play by helping the sender know that the data that's being sent is actually being received. The way this works is the sending host sends TCP segments in bytes, and the receiving host acknowledges bytes received by sending acknowledgments. There is a limit to the amount of data the sending host can send before it receives an acknowledgement from the receiver. This amount is called the window size. The window size is the total number of bytes sent in TCP segments that can be sent before receiving an acknowledgement. Using TCP window scaling, computers are able to achieve large window sizes of up to 1 gigabyte. So as the sending host sends bytes of data in TCP segments, the receiving host returns acknowledgements as it processes bytes received and frees up its buffers. We can see this depicted in this graphic. Let's start by reading the message from the sending host here. Start with byte number 1. I am sending 10 bytes. In this scenario, the 10 bytes is the window size. In reality, the window size would be a lot larger than 10 bytes, since today window sizes are typically 16 megabytes or larger. But this works nicely for this example. So the host is sending 10 bytes, starting with byte number 1. The receiving host, the server here, says, I received 10 bytes, starting with byte number 1. I expect byte 11 next. This is the acknowledgement. The server acknowledges it received the 10 bytes and now is expecting number 11. If we look down here, we can see that in this segment, starting with sequence number 1, 10 bytes have been sent. The receiver sends an ACK 11. Starting with 1, 10 bytes were sent, so the next sequence number it's expecting is an 11. This acknowledgement is sent back to the originating host. Now the originating host sends 10 more bytes, starting with sequence number 11. If we were to ask ourselves, what would be the next ACK that the server would send back to the originating host, we would have to ask ourselves, what's the last sequence number sent? Starting with 11, 10 bytes were sent, so the last sequence number that was sent was 20. So the ACK would be an ACK 21. That's the next expected sequence number. You can see how sequence numbers and acknowledgements, including the window size, make TCP a very orderly and reliable protocol.
All right. And this is what happens when there's data loss and retransmission. No matter how well a network is designed, data loss will occasionally occur. TCP provides methods of managing these segment losses. Among these is a mechanism to retransmit segments for unacknowledged data. So the way this works is computer A sends 10 segments of data. Of those 10 segments, 2 are not don't make it to the destination. The destination acknowledges 3. So 1, 2, it acknowledges, it says, hey, I'm expecting 3 next. And then A says, oh, okay, you need 3. All right, we'll start with 3. And it sends 3 through 10, assuming that there's only 10 packets of data to send. So it sends 3 through 10, and then computer B receives the 10 this time, and then acknowledges 11, saying, okay, I'm ready to go with 11. So that is how data is retransmitted. Now, there's also something called a selective acknowledgement, an Essac. So here in this example, we have 1 through 10 again, 3 and 4 not sent. So if both hosts support Essac, the SAC, if you want, the receiver can explicitly acknowledge which segments or bytes were received, including any discontinuous segments. So in this case, B is replying back saying, hey, I'm acknowledging 3. That's the next one I'm sending. Oh, and also I received 5 through 10. So if once A receives that, it knows that you received, in this case, 1 and 2, because you're acknowledging 3. And then SAC, you also received 5 through 10. So I'll just send 3 and 4, and then the 2 more more segments 11 and 12, which would be the next 2 segments to be sent. And then we acknowledge 13, meaning the next segment of 13 would be sent. That's how that works. Not too challenging. Here is a video talking about this concept. It is 14.6.4, 14.6.4. Let's watch this video.
The graphic depicted in this video uses segment numbers in place of sequence numbers. TCP is a reliable protocol. It uses sequence numbers and acknowledgments to provide that reliability. But what happens when data is lost in transit? As a reliable protocol, there has to be a mechanism for resending lost data so that an entire piece of data, like a file or an image or a video, can be rebuilt from all of the segments. If we look at this animation, we can see this process in action. I'll press play. The source host here sends segment 1 and starts a timer. You can see the timer's running. The destination host receives segment 1 And since it's received segment 1, it's going to send an acknowledgement. Let's see what happens. We can see that the destination host has received segment 1, acknowledges the delivery, and is going to send an ACK2, an acknowledgement 2, requesting number 2. Why? It received 1, so it sends a request for 2 in an ACK2. So we'll see that get sent. All right, there goes the acknowledgement. The source receives the acknowledgement before the timer expires and now can send segment 2. There's segment 2. It's sent, and as you can see, the timer is started. It's going to wait to get an acknowledgement. If it doesn't receive an acknowledgement from the destination before the timer expires, it will resend segment 2. Let's see this in action. You can see the destination has not received segment 2. Since it hasn't received segment 2, it won't send an acknowledgement number 3 back to the device. It's not going to acknowledge that it received 2 and send an ACK3 back to the source host. Let's see what happens. No acknowledgement, the timer expires. You can see here the timer expires. So what will the source host do? The source host will retransmit or resend segment 2 and restart the timer. This time, the information was received by the destination, and now it's going to send an ACK3 or acknowledgement 3 requesting the next piece of data, which in this case would be number 3. The acknowledgement's received before the timer expires, and segment 3 is sent. Segment 3 is received, acknowledged, and a request for 4 is sent in an acknowledgement. The acknowledgement is received before the timer expires, and now the device can send segment 4. Or in this case, it's the end of the transmission. The ability of TCP to retransmit missing segments makes applications that use the TCP protocol very reliable.
Okay, and I feel these videos are helpful. Hopefully you do as well. These videos are inside of NetAcad, inside of the content, but you can also see the videos on the website itexamanswers.net. I've told you about that before. Excellent website. If you are not in NetAcad and you are trying to learn this material to take the CCNA exam on your own without a college class, you can always go to itexamanswers.net, and it has all the videos, all the content from within NetAcad, and hopefully maybe my video isn't that good because it's a video of a video, so you can go directly to the video and see it. Now let's see what that looks like. Let's talk about flow control. All right, so TCP also includes a mechanism for flow control, and this is how it works. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of a TCP transmission by adjusting the rate of data flow between source and destination for a given session. I can tell you what this looks like. So if you've ever sent a file from one place on your computer to another place on your computer, initially that file will start off saying it's going to take an hour. Let's say it's a 1 gigabit file. It'll say it's going to take an hour. And that hour, then like a second later, it says, oh, it's going to take 10 minutes. And then it says 90 seconds and it's done. That's flow control. The same thing happens when you're downloading something from the internet, maybe a file attached to email. Initially, it'll have some big number, and then it will hopefully quickly lower once it realizes that it can expand the MTU, the window size, to a bigger size, and then send more data at one time. Now, it can also go the other way, where the connection is bad, and it tries to send, in this case, 10,000 bits, but it isn't able to send it. So maybe initially it says it's going to take 4 minutes to transfer, but then it jumps to 20 minutes to an hour, and you're like, what happened to 4 minutes? Well, it went the other way. If it goes to an hour, the other side is probably not online anymore. But anyway, so the way it works is there's an initial handshake. It says, hey, we're sending data. It receives the data. So it acknowledges it receives 2920, acknowledges 2920, and the window size is fine, sends more data, acknowledges 4380 and the window size, and on and on and on it goes. The maximum segment size, MSS, is the maximum amount of data that a destination device can receive. A common MSS is 1460 bytes when using IPv4. A host determines the value of its MSS field by subtracting the IP and TCP headers from the Ethernet maximum transmission, or MTU, which is 1500 bytes by default. 1500 minus 60, 20 bytes for an IPv4 header and 20 bytes for TCP leaves 1460. So you heard me say the MTU size, roughly the MTU size, but it's not actually the MTU size. Anyway, so that's what that MSS is. It's the maximum size that it can send of data. Now, what happens if there is data that is congestion on the internet or on the network? It results in packet being lost or discarded. And to avoid and control congestion, TCP employs several congestion handling mechanism, timers, and algorithms. Ultimately, it can make the packet size, the MTU, the size of transmission, the MSS, smaller, and therefore hopefully actually acknowledging just smaller pieces. I also like to give the example on if you're ever talking to somebody and you give them a whole bunch of information and then they say, okay, what's your name? And you give them your name and then they say, now what piece of equipment you're using? Okay, so that person has a smaller MSS and you've got to shrink the amount of data that you got to give them at one time. Okay, it can happen the other way too. You can start off really slow and you can realize the other person knows what they're doing and is like, all right, well, it sounds like you know what you're doing, and then you blur out all you can, and then you wait for an acknowledgement, and the other guy's like, okay, I can fix that, and it's like, oh, okay, you got a big MSS. All right. Now that is everything about TCP. Now we're going to talk about UDP Communications. UDP does not establish a connection. It is connectionless. UDP provides low overhead data transport because it has a small datagram header with no network management traffic. So, and remember, it's using things like IP phones, sending and receiving video streams of data. UDP does not establish a connection between the two. It just sends in both directions. It just sends. Now, UDP, what I mean by both directions, I mean if the sender is using UDP, it's going to send UDP packets without waiting for an acknowledgement. On the other side, the receiver can send without waiting for acknowledgments. But UDP, there are no replies, right? They don't establish a connection, like FM radio, remember? So UDP does not track sequence numbers the way TCP does. UDP has no way to reorder the datagrams into the transmission order. It just delivers them in the order that it was received. And UDP simply reassembles the data in the order that it was received and forwards it to the application. So it shouldn't be reassembles. It should say it just assembles. Anyway, so 1, 2, 3, 4, 5, 6 is sent. It's received 1, 2, 6, 5, 4. That is what's sent to the application layer. It doesn't ask for 3, which is the missing packet. It doesn't reassemble it. It just sends them just the way it is received. Now, UDP-based server applications are assigned well-known or registered port numbers. UDP receives a datagram destined for one of these ports. It forwards the application data to the appropriate application based on its port number. So in this case, we're using port 53 and port 1812 on the server. So UDP client dynamically selects a port number from a range of port numbers and uses this as the source port for the conversation. Remember earlier, you could have multiple protocols running at the same time. You can have multiple DNS requests. You can have requests. You can have multiple TFTP requests. So what it does is it randomly picks one of those ports, the upper range ports that TCP also uses, and the destination port is usually a well-known or registered port number assigned to the server process. That's what it's going to, the destination where it's going. So that would be 80 and 443 and 8080 and 2122. After, in this case, the radius server is 1812. After a client has selected the source and the destination ports, the same pair of ports are used in the header of the datagrams in the transaction. So let's zoom in and take a look at that. So we have a situation where the client one using UDP sends to port 53. That is the destination, port 53. And it uses its port, a random port 49152 as the source. That is received as the server. The server flips those two numbers and sends it back. Then the destination.
I'm having trouble connecting to the internet. It looks like an issue with the router and echo device, so try restarting them. Unplug both of them, then plug the router back in. Wait 30 seconds. Once the router is back on and connected to the internet, plug in the echo device.
Let's hope that I haven't lost internet. There's been a storm, and hopefully you guys are still with me. If you are, please send somebody type something in the chat room just so I know that you're still there. Anyway, so okay, great. All right, super. My Alexa has lost connection, not my computer, which is awesome. Anyway, so the client sends destination port 53, source port 49152. Server receives that DNS request and sends back the information by flipping it, just like IP, just like TCP did. It flips it, sends it back, so the destination becomes 49152, and the source port is 53 because that's the server. On the other side, we're doing a radius request. So the client sends a message with a destination port 1812 and a source port, in this case, random number in the upper range of 51152. The server receives that radius and then replies back with the data on destination 151, 152, 14, 18, 12. Okay, let's get out of that slide. Server responses to UDP clients use well-known port numbers as the source, obviously. And that is the end of this presentation. So let me stop sharing. Hopefully, as I said at the beginning of the presentation, these concepts are not that hard to understand. The most important thing is understanding TCP is connection oriented and UDP is connection less. TCP establishes a connection and then waits for all of the data to be sent or requests the resending data. UDP just sends the data like FM radio, and if it is not received, there's no retransmission. It's just not received. If there is any request for missing data, it is made by the application layer in UDP. It doesn't mean just because UDP does not acknowledge data doesn't mean the application itself can't look for missing data. All right, so that is the end of that process, that presentation, module 14. My name is Don Lafond, Professor Don, and it's been my pleasure teaching you today. If you have any questions and you're here with me live, I will give you a moment to ask those questions before I go on to module 15, which I'm also doing tonight. If you are watching this as a recording inside of our NetAcad classroom, please ask questions in the help discussion forum. And if you are on YouTube, please ask questions down below in the comments section. Also, please rate and review and follow me on YouTube so you can get a notification of all of my future presentations, and I do appreciate it when you do that. All right, been great being here with you, and I'll see you again in a few minutes if you're here with me live, or I'll see you in the next video if you're watching me as a recording. Thank you, and have fun learning Cisco.